Multivariable Calculus, Section 13.9, Change of Variables. Let's review U substitution from single variable calculus. Here we have an integral which is difficult to integrate, and so what we do is we do a change of variables, which we call U substitution, by setting u equal to the inside function, and then du is 2x dx, and this is a good candidate for U substitution because the variable part of du is sitting there in the integral. Move the 2 to the other side, and now we can substitute a half du for x dx. We can substitute u for x squared plus 16, and then we can also change the limits to match u. When x is 0, u is 0 squared plus 16, and when x is 3, u is 3 squared plus 16. Now, if we take a look at the picture of the first integral, there's the function x times the square root of x squared plus 16. And so the integral returns a value that is equal to the area of region R. And then here we have the graph of 1/2 square root of u from 16 to 25. And so region S is the area of region S is the value returned by that second integral, and of course these two values will be the same, and so the area of R and the area of S are equal. Now we're going to define t as a transformation from the UV plane to the XY plane. So here we have a UV plane with a nice vertically and in fact horizontally simple region divided into subregions, and t will transform that net, I guess you could call it, into a curvy net on the xy plane. And so the lines, the horizontal vertical lines on the UV plane become curvy lines on the xy plane, and the region S becomes a curvy region R, which is neither, in this case, vertically or horizontally simple, and so it would be hard to integrate over this region for that reason. Now what we really want is t inverse, to transform the curvy region in the xy plane that we're having difficulty integrating and make it a simple region in the UV plane, and so that would be the inverse operation, t inverse, and that's what we really need to make our integral easier when we have a difficult region that we're integrating over. So here's a picture of it. T sends UV to XY. XY is called the image of UV under the transformation T. If every point in the region of the UV plane that is in the domain of T has a unique image in the XY plane, then T is called one-to-one. It's a one-to-one function, and that, of course, is what you need. Otherwise, you won't have an equivalent integral when you do the change of variables. The U curves in the XY plane are images of horizontal lines in the UV plane, usually. And the V curves are the XY plane images of vertical lines in the UV plane. And so here's a picture of a not-so-nice region on the XY plane with U curve and a V curve going to a particular point XY. And then what we are trying to do is find an equivalent region that is vertically or horizontally simple in the UV plane, in this case a rectangle, which is very easy to integrate over. And then T inverse then takes the point XY over to its image, UV, in the UV plane. Let's review a little bit. T computes x and y from u and v, and T inverse computes u and v from x and y. In other words, T gives you a formula for x and y in terms of u and v, and T inverse gives you formulas for u and v in terms of x and y. Now, it's not really important that you remember which is T and which is T inverse. It'll be obvious which formulas you need as you go through the problems. And if you're given a formula for u and v, you can always use algebra to get a formula for x and y. But the next question is, how do we change dA, which is equal to dx dy, from our nasty integral that we want to simplify into terms of u and v? Because not only do we have to substitute for x and y in the integrand, we need an equivalent for dx dy. Now recall that in single variable calculus, dx was equal to something times du. Almost always you had something there. And this something was necessary in order to write the instantaneous change along the x-axis in terms of u. So now we need to change the instantaneous change in area with respect to x and y into something equivalent with respect to the changes in u and v. So with two variables, we need to explore how to write dA, the instantaneous change in area, in terms of u and v. There will be something extra other than just du dv. And it won't be magic, it'll be math. So dA is the instantaneous change in area on the xy plane. And we have our u curve and our v curve. And how do we get from here to area, little teeny tiny changes of area along the surface? Well, if you'll recall, if you cross vectors, you get areas of parallelograms. So we're going to use that idea. So here's the velocity vector along the u curve. We'll call it tu, and of course we compute it by the partial derivative of x with respect to u times I, plus the partial derivative of y with respect to u times j, or in Newton's notation, xu comma yu. And then we have a vector, a velocity vector along the v curve, and we'll call that t sub v, and we compute that with the partial derivative of x with respect to v times I, plus the partial derivative of y with respect to v times j, or in Newton notation, xv comma yv. Now, we can approximate curvy regions in the xy plane with parallelograms determined by the velocity vectors along the u and v curves. And then, of course, if you have parallelograms and they shrink down to nothing, then the areas are equivalent to the instantaneous changes. So as the changes in u and v shrink to du and dv, we get dA, the instantaneous change in area. So now we need to get a formula for the area of the parallelogram. And so we'll begin by just dotting the velocity, crossing the velocity vectors. And here's my determinant to do that. Notice that there's no k component here because we're just going along a flat surface at this point. And there's my augmented part of the determinant that I used to compute it. And all the diagonals are 0 except those two shown. And so we get xu yv minus xv yuk. Now notice that we need the length of that vector cross product, and so we just take that quantity squared and square root it, and so we get the absolute value of that quantity. Now that can be written as a simple 2 by 2 determinant. And then there's also another notation that's introduced in this section, partial of x comma y with respect to partial of u comma v. And that notation indicates that if you want to make the determinant out of it in order to compute it, that the top, the variables in the top are the rows, delineate the rows, and the variables in the bottom, in the denominator, delineate the columns. So we now have the change in area equivalent to, change in area which is dx dy, equivalent to this determinant times du dv. And of course we have to make up a name for that. Okay, so we're going to name this determinant that we've developed the Jacobian. The Jacobian of the continuously differentiable transformation t that maps the uv plane onto the xy plane is the real valued function j sub t, which is in fact just equal to the determinant that we developed on the previous slide. Notice that the Jacobian takes information from the uv plane and creates a real valued function in u and v from that. So here we have our original integral with x and y, and we take the integrand, the function, and replace x and y with the equivalent expressions in u and v, and then we replace dx dy with the absolute value of the Jacobian times du dv. Now notice that the absolute value is around the Jacobian because where did we get this determinant from originally? It was shorthand for the length of a vector. The length of the vector is the area of a parallelogram, and so it has to be positive, but the determinant could come out negative, and so we have to take the absolute value. Note, we use the absolute value of the Jacobian because the length of a vector, aka the area of a parallelogram, is always positive. So just in case the determinant comes out negative, you got to take the absolute value. All right, now that took care of change of variables in double integrals with x and y. What if we have a triple integral in x, y, and z? Well, it's the same idea. We have x's in the first row, y's in the second row, and z's in the third row. We just add a third row and a third column for z and w. And the notation for that, the new notation, is the partial of x comma y comma z with respect to the partial of u comma v comma w. So it's just shorthand so they don't have to write out the determinant. Notice that the variables in the numerator delineate the rows, and the variables in the denominator again delineate the columns. And so it's the same idea. We take our region in space that is not amenable to being set up for the integral. We do a change of variables on those x, y's, and z's in the integrand, and then we multiply that times the absolute value of the Jacobian times du dv dw. So the same idea. Unfortunately, calculations are more difficult. The more variables you have, if you get into quadruple integrals with 4 variables, man, it gets really rough. Need a computer to do that. Okay, so revisiting U substitution with this Jacobian idea in mind. How does this match what we did in single variable? It seems completely different, but actually it's not. So here's our example again from the first part of the lesson. And I'm going to set it up a little bit differently this time. I'm going to let u equal x squared plus 16 again, but this time I'm going to solve for x. And notice that x is the positive square root of u minus 16 because we're going from 0 to 3, so x is positive. And then dx du, use the chain rule to compute that. And so this time, you can think of dx du as the Jacobian. It's a 1 by 1 determinant. Okay, instead of a 2 by 2, it's a 1 by 1, so it has 1 entry. So think of that as a 1 by 1 determinant. And so if we set it up in the light of the Jacobian idea, we have a substitution for x is the square root of u minus 16. Substitution for the square root of x squared plus 16 is square root of u. And then we should have a Jacobian and times du. And what's the Jacobian? Well, there's x. There's the square root of x squared plus 16. Dx is the Jacobian times du. And the Jacobian is just dx du, because see, look, dx du times du is just dx. So we substitute the formula in terms of u for dx du, and look what cancels. And we end up with exactly the same thing that we got much faster in single variable calculus with what was actually a shortcut. All right, now we're going to look at some examples. Given, this is number 2 in your text. Given u equals x minus 2y and v equals 3x plus y. Part A, solve for x and y in terms of u and v. Okay, so we've got a formula for u and v in terms of x and y. Is that t or t inverse? Doesn't matter. B, compute the Jacobian. All right, so we're going to use, this is algebra. This is probably the hardest part of these problems, is switching the formulas around. So we're going to use linear combinations. So I took the second equation, multiplied by 2. That way I can get the y's to drop out. And then I can solve for x in terms of u and v. And we'll do the same thing, except this time I'm going to multiply the first equation by -3 so that I can get the x's to drop out. And then I can solve for y. Ta-da! Get your algebra polished up, folks. It's going to be a rocky ride. Okay, the Jacobian is easy then, because we just need, there's the new notation. We just need our determinant, and all the derivatives are numbers. So super easy. Number 6, given u equal 2x over x squared plus y squared and v equal negative 2y over x squared plus y squared, solve for x and y in terms of u and v, and b, compute the Jacobian. So similar to the last problem, only this time the algebra is a little trickier. You have to give it a little thought. I'm looking at this and I'm noticing the squaring in the denominators, so that gave me an idea. So I squared u and v and added them together, and that gave me, when I simplified it, u squared plus v squared equals 4 over x squared plus y squared, or if you flip it over, x squared plus y squared equals 4 over u squared plus v squared. Now, I could substitute that then for x squared plus y squared in the denominator, and in that first equation, everything would be in terms of u, v, and x, so then I could solve for x. Then I did the same kind of thing in the v equation, which eliminated x from that equation, and I was able to solve for y in terms of v and u. I didn't show every step there, but it's the same idea as the first part. Ta-da! Okay, so now for part B, we're ready to do our Jacobian, which is this determinant. And I have to apply the quotient rule 4 times. Partial derivative of x with respect to u, partial derivative of x with respect to v, and then in the bottom row, partial derivative of y with respect to u, and the partial derivative of y with respect to v. You may want to pause the video and compute those yourself. It's a little bit tedious. So now we have a big mess we need to simplify. Let's start a new slide. And we'll simplify what we've got there. Simplifying, 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 simplifying. Isn't algebra fun? Still a bit messy, but there's going to be a happy ending. Hold on. So now we need to evaluate the determinant by multiplying the top left times the bottom right minus the top right times the bottom left. And then we multiply out the quantity there on the left and collect like terms. And we get something very nice. That numerator will factor. You can factor out of 4, and then what's left factors into, guess what? V squared plus u squared. And so we can reduce it again and get a very, very nice Jacobian as our final result. Ta-da! Number 8, substitute u equal xy and v equal x over y to find the area of the region bounded by these 4 curves. So let's sketch that first. In blue, we have y equal x and y equal 2x. And in black, we have the parts of the hyperbolas, x, y equal 1 and x, y equal 2. And here's our handy-dandy formula, but we're just doing areas, so our functions, our integrands, are just 1. So all we need is a Jacobian. Now, we need formulas in x and y in order to compute our derivatives, so I notice that if I multiply these two together, the y's will cancel. And so x is equal to the square root of u times the square root of v, positive because we're in the first quadrant. And then if I flip v over, the x's cancel and I get y squared, and so I can solve for y in terms of u and v. Okay, so now we're ready to compute our determinant, which is the Jacobian. And notice that when we take the derivative with respect to u, we treat v as a constant, and when we take the derivative of y or x with respect to v, we treat u as a constant, so we don't need the product rule. And we end up with negative 1 over 2v, but we have to take the absolute value, and we're going to be using positive numbers, and v is positive, so we're going to have to eliminate that negative 1. So we're going to use the absolute value, which is 1 over 2v. Now, just for fun, I found the intercepts of the 4 curves in the xy plane. Turns out we don't really need that, but I thought it might be interesting to map those onto our new region. So here's our original region in the xy plane, and here are the equations of the curves, and here are our formulas for u, v, x, and y. Now notice that xy equals 1 and xy equal 2 and u equals xy. So that means that some of our curves are easy because u is equal to xy and xy equals 1 is one curve and xy equal 2 is the other curve. So two of our lines on the UV plane are u equal 1 and u equal 2. So that was kind of easy. Now we need to use information for the line y equal x. We just set those two quantities equal to each other. And the u to the 1/2 divides out. And then if I multiply both sides by v to the 1/2, I get v equal 1. So there's another curve, aka a line, in the UV plane. Now we only have one more, and that's y equal 2x is the only other one we have to change. And so similarly, I just set y equal to 2x using our formulas for x and y in terms of u and v. And then note that the u to the 1/2 cancels again, and we get v equal 1/2. So those are our four curves, aka lines. See, we're going from curvy stuff to linear stuff in the UV plane. So there's a picture of it, and we can see the coordinates of the corner points easily from this, but let's see how they map on. So 1, 1, if we have 1, 1 for x and y, then u is 1 times 1 and v is 1 over 1. So that's that point. And then root 2, u is root 2 times root 2, x times y, so that would be 2 for u. And v is root 2 divided by root 2, which is 1. So that's the point, 2, 1, and so on. So that's how that area maps onto our new plane. All right, so all the preliminaries done. We're going to integrate for u going from 1 to 2. We're going to integrate v going from 1/2 to 1. And go back to our original problem here. U is going from 1 to 2. V is going from 1/2 to 1. We got our Jacobian, absolute value of Jacobian du dv. Integrate that with respect to u and evaluate u from 1 to 2. And then integrate 1/2 times 1 over v, which would be 1/2 log of v. Plug in your v values. Simplify your answer using the laws of logs, and we're done. Number 10, find the area of the region bounded by y equal x squared, y equal 2x squared, x equal y squared, and x equal 4y squared, so 4 parabolas. Hint, let y equal ux squared and x equal vy squared. Took a genius to do that. Okay, so here's a picture of our region in pale blue there. Okay, so let's substitute ux squared for y, and we get x equals vu squared x to the 4th, and then you can solve for x by dividing by x and then moving v and u to the left, and there you have x. Yay! Now let's do something similar. Substitute vy squared for x in the first equation, and then similarly you can solve for y. All right, so now we're good to go on the Jacobian. Again, remember which variables are treated as constants each time you compute the derivatives. If you want to freeze the video and check that out, you may. Otherwise, we'll just move on. So there's our handy-dandy Jacobian, and it's definitely positive. Now, we can also solve for u and for v, which we need to do for later. And so since x is equal to 4y squared, we can substitute there, and we get v equal 4 for one of our new boundaries in the UV plane. And similar, we can do something similar. I'm not going to show you each and every step, but basically do similar things to figure out the other boundaries. And so we end up with these 4 lines. So the area then is going to be the Jacobian times dv du, and v is going to go from 1 to 4, and u is going to go from 1 to 2. And I didn't bother drawing that area for you. So now we just need to integrate that with respect to v first. we get negative v to the negative 1 evaluated from 1 to 4. And then we have to integrate with respect to u and evaluate that from 1 to 2. And we get 1/8 for our final answer. That wasn't so terrible. Well, maybe it was. So now I want to do a slightly different problem. Evaluate the integral x, y, dA by A using change of variables and B by splitting the region R into two regions, given that R is the region in the first quadrant bounded by these four curves, and transformation T is defined this way. Sketch the region R in the xy plane as well as the transformed region S in the UV plane. Okay, so the reason this is different is, first of all, we have an integral. It's not just one. We're not just doing the area. We're integrating over the region the function z equals xy. So that's going to be a little different. And then there's a few other things that come out differently, as you'll see. And also, we're going to check our answer using change of variables by doing the original problem without a change of variables by splitting the not so nice R region into regions that are simple and can be handled. Okay, so here we go. Here's a picture of the original xy plane with our four boundary lines, and we have a nice area contained by those boundaries. And just for fun, I found the intersection points. Now let's use our transformation to get back to formulas in terms of u and v. So x is u over v and y is v. So I just substituted y for v and then solved for u. So now I have expressions for u and v because v equals y and u equals x times y. So I can find the intersection points for my uv plane very easily because v is just the y value, and then to get the u value, I just multiplied the two coordinates together. All right, now we need equations for the boundaries in terms of u and v. And so we just substitute v for y and u over v for x in the first two equations and solve for v. And then for the second two, for the hyperbolas, since xy is just u, we get u equals 1 and u equals 3. So there's our region in the UV plane, R on the XY plane, and S on the UV plane. So we've done the drawings, and now we're ready to integrate with respect to U and V. So here we have S, and we're going to integrate U from 1 to 3, and we're going to integrate V from root U to root 3U. And we need to substitute for the integrand xy, which is just equal to u. And now we need to do something about dA. So we need the Jacobian. And here are the equations for x and y. So we compute the partial derivatives and cross multiply and get a very nice Jacobian. So now we have the integral from 1 to 3 from root u to root 3u of u, which took the place of xy, times the Jacobian 1 over v times dv du. And we can integrate 1 over v, make it log v, and then we have to substitute these limits. So we get this nice expression. And then we can use the laws of logs to rewrite log square root of 3u as 1/2 log 3 plus 1/2 log u, and then rewrite log square root of u as 1/2 log u. And look, that cancels. Isn't that nice? And then we can integrate with respect to u, and we get our constant multiplier, 1/2 log 3 times 1/2 u squared, evaluated from 1 to 3. And when we simplify that, we do, in fact, get the same answer as we will get when we do the original one in two parts, we hope, at least. So let's take a look at part B and see if we do, in fact, still get 2 log 3. We better, huh? All right, so back to the original area, and we're going to split that in two, and now we have two simple regions. The first region, we're going to integrate from 1 over root 3 to 1 along the x-axis, and from the bottom parabola, 1 over x, to the top line, 3x, for y. And then the second half, second area, x is going to go from 1 to root 3, and y is going to go from that bottom line, x, up to the top parabola, 3 over x. All right, you ready? Integrating with respect to y, we get a half y squared in both of the integrals, and we evaluate using those variable limits. So it's a little bit of algebra there. I won't go through that unless you want to stop the video and check it out. And then we integrate with respect to x, which is a little bit easier, and plug in the values of the limits. And I didn't show all of that, but you do in fact get 2 log 3. Ta-da! Not magic, just math. One last little tiny comment. Conveniently, the Jacobians in all of our textbook examples just happen to come out positive. If by some horrible accident one should happen to come out negative, say on a quiz, please don't forget to take the absolute value. Bye-bye for now. Happy calculating. We want to integrate over an extremely irregular figure. We need a way to change it, or we'll err. We need to change the variables x and y in u and v terms, or our efforts will never ever end. The Jacobian of u and v is a determinant. X, U, X, V in the first row, Y, U, I, V in the second. And it's used with the U, D, V instead of the X, D, Y. We write the integrand, that's why. You can equal one of the curves and be the other, I've heard. It's more complicated, don't be